Morning. Oh, it is going to be afternoon. So let's get it going. Okay, so just as a reminder, there are no ed puzzles for lab tomorrow that are due tonight. And there's no lab quiz going to happen at the start of lab tomorrow. The lab tomorrow is an equilibrium lab, which we are going to start the discussion of today. And I will be typing up homework 7 tomorrow during lab, and it'll be due Sunday at 11:59 p.m. It'll be over the material we covered today. The last thing I wanted to mention are bonus opportunities. There are several bonus opportunities. They're in the very first content folder at the top of the screen. But I wanted to discuss what you got to do to get those points. One of the bonus opportunities is that you can go to the scheduled Chalk Talks for the semester. If you go to a Chalk Talk, you can turn in notes over what you hear, and that is 5 points. I believe the next Chalk Talk is during X period, and then the last one's in the evening, or vice versa. I can't remember which is which. Another opportunity to earn some bonus points is that you can donate food to the Bear Food Pantry. And the way you're going to accomplish bonus points from that is you will take your donation over to the food pantry. I used to have it just delivered to me, but it's hard for me to get it over there. So take your donation over to the Bear Food Pantry. You're going to take a selfie turning it in. And you're going to tell me how many cans or items you donated. It's 1 point per item you donate, up to 10 points maximum. The next thing that I know for certain is that I'm going to offer is I've got to get it together. Hopefully by next week, I will be putting together a list of scientists' names, and they are just that. They're scientists of a variety of backgrounds. It's not just chemistry. And I have a PowerPoint slide. Basically, you get a picture of them, and then you write in your own words a little bit about their accomplishments. It's a half page, is all it is. It's not a big thing. It's a half page thing. So, and that will be worth 10 points because you got to do a little bit of research for it. So that will be coming up. And again, and the maximum number of bonus points you can earn is 30 points, which is a 3% curve. So folks, when it comes down to that end of the semester, if you are 3.5 points away from the next letter grade, don't ask. If you've done all the bonus, that's 3% curve already. So keep that in mind. And tomorrow I'll be passing back 2 labs and your exam. The grades I know got posted today. You're welcome if you're just desperate to follow me back to my office, but I figured I'd be seeing you all tomorrow, and I really wanted to get started on the material that we need to cover. Any questions? If I can, it'll be tonight before I can get it going. It's just been one of those weeks. Any questions? Any other questions? Yes. Will you be posting the bonus opportunities? They're already posted, except for in the very first folder when you go under classroom, online classroom. That very first folder is bonus. So whenever you post like the scientist names, though, it will go into that folder, and it'll have like what we're supposed to do for it. Yes.
Did you say that there was something due before lab tomorrow?
Nothing new before lab tomorrow.
Good, I want to see that.
No prelim, no quiz, no ed puzzles. Any other questions? Okay. Then we are going to get into today's information. Today, my goal is to cover reaction mechanisms. We will talk about equilibrium equations and constants. I may or may not briefly discuss KC-KP relationships, but I will be getting into calculation of equilibrium constants. So the very first thing is the reaction mechanism. Folks, we've already discussed collision theory. And as we discussed, it's very unlikely for three molecules to collide with the correct orientation, with the correct energy, all at the same time. And so the reason I'm bringing up that particular comment is it means that the rate laws for chemical reactions rarely reflect the coefficients of the chemical reaction. So you can't simply look at the balanced chemical equation and develop a rate law. Rate laws have to be determined experimentally, which we've already talked about. That's using the method of initial rates and also integrated rate laws. Now, once we've gone through and determined the rate law experimentally, as chemists, we know that we know that the reaction may not match coefficients to rate law. So we develop what's called a reaction mechanism to help explain what we are observing. A reaction mechanism is nothing more than a series of steps. Those steps are referred to as elementary steps. And these series of steps describe a possible scenario, a possible pathway by which the reaction will occur. Now, in order for a reaction mechanism to be valid, it has to have two factors. Number one, the elementary steps have to add up to the overall reaction you are studying. And number two, the rate law determined from those elementary steps has to equal the rate law that you determined experimentally. Now, again, these reaction mechanisms are set up of a series of steps. Those series of steps are referred to as elementary steps. Elementary steps, folks, can be unimolecular, which means that a sole molecule is responsible for the speed of the reaction. They can be bimolecular, meaning two molecules are responsible for the speed of the reaction, or they can be termolecular, but as we've already said, termolecular is less likely than bimolecular or unimolecular, simply because it's very difficult for three molecules to collide with the correct energy at the correct orientation. Now, when developing the reaction mechanism, the reaction mechanism can contain intermediates and they can contain catalysts. The question is how are you going to recognize when you're looking at a reaction mechanism what the intermediate is and what the catalyst is? An intermediate will be a material that is made in one reaction and then it gets used up in a later reaction. A catalyst is going to be a material that's added in one reaction that is made later on in a later reaction. And all of this is in the PowerPoint and the video. Oh. So, again, the only way to determine a rate law is through experimentation. And that rate law will be the rate law for the overall reaction. The rate law determined for the overall reaction will not necessarily be related to the coefficients of the balanced chemical equation. However, we can also write rate laws for our elementary steps. And if you write a rate law for the elementary step, then the rate law of the elementary step is based on the stoichiometry. And we will take the reaction mechanism and we will look to the slow step in the reaction mechanism to identify our rate law. Oh, allergies, so long. So again, a reaction mechanisms is just a series of elementary steps that when you add all those elementary steps together, you get the overall reaction. You can write a rate law for the elementary steps, and a rate law for the elementary steps is based upon the coefficients of the reactants. You cannot simply write a rate law for the overall reaction. The only way to determine the rate law of the overall reaction is to determine it experimentally. And it does not necessarily have the coefficients. One thing I do want to point out that may not have been stated clearly previously is that when we look at the rate laws are based only on the reactants in a typical reaction. Now, we will come across rate laws where we do have to take into account the products, but that only occurs if we're talking about a reaction that is in equilibrium. But when we get to the end result of a rate law, when you're totally done, it will only include reactants. Okay. So let's look at examples of reaction mechanisms, and we are going to use our terminology. As we're doing so, we are going to develop the rate laws of elementary steps, and ultimately we will develop the rate law for the overall reaction and determine the overall reaction. So let's just take something very generic. X plus Y is equal to M. I mean, not equal, goes to form M. And this is the slow step. That one is then followed by X plus M going to form Z, which occurs quickly. These are elementary reactions, elementary steps. To get the overall reaction, you're going to perform a calculation or perform a problem very similar to what you did with Hess's law in College Chemistry 1. In other words, we're going to cancel out anything that's on the left and on the right. So, since M appears on the right in the first equation and on the left in the second equation, the M cancels out in writing the overall equation. So the overall equation will be 2x plus y goes to form z. M by definition would be an intermediate. Because it was made in the first reaction and then used up in a later reaction. Now, elementary step number 1 would be called a bimolecular elementary step. Except I can't spell. It is bimolecular because 1 plus 1 makes 2. The second elementary step is also bimolecular. Because again, 1 plus 1 makes 2. Now, we can write a rate law for elementary step 1. And we can write a rate law for elementary step 2. Because we're talking about the rate laws of the elementary step, the rate law is going to use the coefficients. So it would be x to the 1, y to the 1. The rate law for the elementary step number 2 is going to be rate is equal to k times x to the 1, m to the 1. So when you write a rate law for an elementary step, you're just using the coefficients as the exponents. Now, a rate law is based off of the slow step. The rate law for the overall reaction is based on the slow step. If the first elementary step is slow, then the rate law of the overall reaction will equal the rate law of that step.
And folks, if you are taking notes and you have some way to make notation, however you do it, I would highlight that statement. So what that means is since our first step was our slow step, that means that for 2x plus y goes to form z, our overall reaction, the rate law is going to equal k times x times y. Because that was the rate law for the slow elementary step.
Love it, slow.
Again, you have to remember that these steps are proposed mechanisms. The only way to know that that step was the slow step, if you will, is if we were to have been able to compare our determined rate law using this method to the experimental one. In other words, we don't know if it's slow or not. Definitively. We're saying it's slow. We're going to determine if this step is slow, we're saying, hey, if it's slow, what would the rate law be?
So,
Does it match the experimental?
so that would be given to us and then it's.
Yes, in class, it has to be given to you. You're not gonna know it's slow unless I tell you it's slow.
Do you have, oh, in a minute, sorry.
So let's look at another possibility. I'm gonna give you time to do this one. We're going to have the reaction, y goes to form M. And that's gonna be a slow step. We're going to have the reaction M plus X goes to form N. This is going to be a fast step. And we're going to have N plus X goes to form Z, which is going to be a fast step. What you need to do is I want to know the molecularity of the elementary steps. The rate law for the overall reaction. The identity of any intermediate. The identity of any catalyst. The overall reaction. And we'll go with that. Okay, this one should have been fairly straightforward. The first reaction mechanism we're proposing is unimolecular because there's only one reactant. The second and third reaction are bimolecular because there are two reactants in each. The rate law for the overall reaction is based solely on the slow step. And the slow step is the first step. So the rate law is going to be rate is equal to K times Y. Because the rate law had to be equal to the rate law of that elementary step. M and N are intermediates because they're made from a reaction and then used up in the next in a later reaction. Folks, it doesn't have to be the next reaction. It just has to be made in one and then somewhere below that used up. As a reaction. There were no catalysts in this reaction. And then the overall reaction was the same as the one before, which was 2x plus y goes to 1z. Questions? Okay, now. If the slow step is not the first step. That's what we're gonna look at now. So let's see, I have one that is going to be 2 nitrogen monoxides that are gonna set up an equilibrium to make N2O2. And that is gonna be a fast step. And then the N2O2 is going to react with hydrogen to make N2O plus H2O in the slow step. And the N2O is going to react with another hydrogen to make N2 plus water. And that is also a slow step. All three of our elementary.
Has been issued for your location.
All three of our elementary steps are bimolecular. Because all three of the elementary steps have two reactant molecules. Even though this first one only has one reactant because of its coefficient, that made two. The overall reaction for this would be 2NO plus 2H2 goes to make N2 plus 2H2O. N2O2 and N2O are intermediates. I got all the easy stuff out of the way first. Now, we need to deal with the fact that the second step is the slow step. We're going to start the same way, folks. You are going to start by developing the elementary rate law for the slow step. Which in this case is going to be rate equals K times into O2 times H2. Now, rate laws for overall reactions cannot contain an intermediate. So we have to figure out where the N2O2 came from. Well, it specifically came from reaction 1. Now, if I were to look at the rate law, for
1801 has been issued for your location.
that's gonna drive me crazy. But I understand. The rate law for reaction 1 is going to have 2 parts. Because if you look back, what you will see is that it has this double-headed arrow. And that double-headed arrow means equilibrium. Now, when you have a reaction at equilibrium, it means that the rate of the forward reaction equals the rate of the reverse reaction. So let's just break this down. We're going to have a forward and a reverse. So the rate of our forward reaction is going to be determined the same way we've been doing it, where we take that rate that is, and that's going to be equal to K times the reactants of the forward reaction, which in this case, the reactants of the forward reaction is NO squared. But this reaction is at equilibrium. If it's at equilibrium, then you can also have the rate of the reverse reaction. And if you have the rate of the reverse reaction, if you have a reverse reaction, who are the reactants? The products. So for the reverse reaction, that would be equal, rate is equal to K times N2O2. Because it's always the reactants. So for the forward reaction, it was the reactants on the left. For the reverse reaction, it would be the reactants on the right. Now, we said that rate forward is equal to rate reversed because this is at equilibrium. So that means that K NO squared is going to equal K into O2. Now, why did I start this? Does anybody remember why I started this? Your rate law can't have an intermediate. And our rate law had the N2O2 intermediate. So what we're going to do is we're going to solve this rate law, this equivalent rate law, and all of our K's are going to become just K. It doesn't matter that they're forward reverse, they just all combine together to form one rate constant. NO squared is going to equal to N2O2. Folks, I now know what N2O2 is equal to from my original equation up here. So I can plug in for that N2O2. So the rate is going to equal K times K times NO squared times H2. Again, the K's are going to combine to form one thing. So this becomes rate is equal to K times NO squared times H2. This would be the rate law for the overall reaction. And it would be true as long as the experimental rate law came up with the same thing.
On your, you wrote out the elementary expense, next to that was slow, or you just take the first one.
Did I? I didn't mean to. There will only be one slow. There's only going to be one slow step. Sorry, that third one was supposed to be fast. Folks, what does that mean from a perspective of a energy of activation diagram? It means that the first one's going to have an E sub A, yes, but the second one's going to have a bigger E sub A. And then the third one will have an E sub A. So this reaction may have looked like this. It has, this was the first step, which was fast. So small E sub A. The second step was slow. So large E sub A. And the third step was fast. So small Issa Bay. I'm gonna give you one to do, and then our break will probably come. So. Assuming. The catalyst. Is in the rate determining step. Because that's what we would want catalyst therefore is to speed up the reaction. What's the rate law? The question is who's the catalyst? Remember, a catalyst is something that is used up in an early reaction. And is made in a later one. Huh? Magnesium 2+ is your catalyst. Because it was used at the beginning and it was made at the end.
So then I'll also be there.
No, intermediates are made at the beginning and used up at the end.
Okay.
So it does depend upon how it's done. So in this case, manganese 3+ is a intermediate, manganese 4+ is an intermediate. Because they're made at the beginning and used up later. But Mn2+ is your, oh, I just realized. Mn2+ is your catalyst. Whereas Mn3+ and Mn4+ are the intermediates. And this overall reaction therefore would be 2Ce4+ plus Tl+ goes to make 2Ce3+ plus Tl3+. And the rate law is going to be K times the Ce4+ times Mn2+. You can have a catalyst in the rate determining step. Rate law, you should have a catalyst. Yes.
So the catalyst is including like all the not.
Right.
Catalyst already very well.
Probably. Because it affects the slow step. Otherwise, you would have a much higher E sub A because of the because manganese, I mean, cerium would have to just lose an electron all on its own. And it's not likely to occur.
Will we ever see a catalyst like the second step?
If it's a slow step, you might. It all depends. So yes, you can see a catalyst anywhere. It's just catalysts come in somewhere up above and are made at the bottom. That's all you just gotta know that that's the process. Okay, my phone didn't ring because I'd originally taken off the timer. So you have a couple of minutes. I took away that timer because of the test Monday. I didn't want to interrupt it. And then we're gonna get it. Whatever we got. Just easy.
So it gets rid
They
of,
don't.
it just turns into one.
It just turns into one. So you can think of it as K forward and K reverse.
Oh, so it's not so much like. And then it's bigger. You're just. Thank you.
Won't be long. Yeah, I've been there. I used to go to those RA where they would when the RAs were going through their various processes to become an RA. We had to do the conference, we interviews. Yeah. Yes. You have basically time to be. Currently it's National Pig Day, in case you didn't know. Brothers. We're taking. Yes, is it well crafts? But they like read it in where it's like. It's to the front, yeah, but it's so. It's not like. Okay, I'm gonna go ahead and get started and get us into this. First of all, we're going to be talking about the equilibrium constant and the equilibrium expression. The equilibrium constant is just represented with capital K. You will see variations of the equilibrium constant where there is a subscript to the right of the equilibrium constant K. Those variations are just indicative of what it is talking about. So a common one that we're going to encounter is going to be Ka when we start talking about acid chemistry, Kb when we're talking about base, Kw is the equilibrium constant of water. Later in the semester, we'll talk about KSPs. Those are for anything that is a solid. So solids do dissolve at least a small amount, and the solubility product is what's going to tell us. And then the others are just generic. So KEQ is often used just to say, hey, I'm an equilibrium constant. KC is often used to say, hey, you're going to be talking about concentrations. They're just generic terms. Now, when we write the equilibrium expression part of our equation, you are only going to include aqueous solutions and gases. The reason you only include aqueous as in gas materials is because those are the only substances whose change in amount can have a dramatic effect. We don't include solids because the change in the solid quantity is not going to have a dramatic effect typically. We don't include pure liquids because a pure liquid's changing amount is not going to have a dramatic effect. So again, we only focus on the aqueous and the gases. Now, The equilibrium constants do tell us something. So let's just look at it from a number line perspective. Greater than 1, less than 1, and that's supposed to be just a good old 1. What the equilibrium constant describes is the amount of reactants compared to products. When you have an equilibrium constant that is greater than 1, you can expect a significant amount of product. So in other words, the greater the K, the closer the reaction goes to completion. The greater the K value, the closer the reaction goes to completion. When you have an equilibrium constant equal to 1, it means you have equivalent amounts of reactants and products. That's the only way you're going to get a 1. And finally, we're not talking a negative value here, folks. Equilibrium constants, just like Kelvin, just like time, just like concentration, they can never be less than 0. But you can have really tiny numbers like 10 to the minus 14, 10 to the minus 30 something. When you have equilibrium constants that are less than 1, it means that the reactants are primarily present. So it means the reaction doesn't do much at all. It just sits and stares at it for the most part. Simply there's a sliding scale here. Again, the bigger that number is, the more likely it goes to completion. The most likely then it just sits and stares at you. So when we write the equilibrium expression, let's just take our generic reaction of A plus 2B. Whoops, didn't even do that yet. Goes to form 3C plus D. When you write an equilibrium expression, the expression always starts with your capital K, which is your equilibrium constant. That equilibrium constant is going to be equal to the products over the reactants. So for this reaction that is our generic reaction, our K is going to be equal to C, the concentration. Again, remember brackets, it mean concentration. And it's going to be raised to its exponent, raised to its coefficient. So C3D, that's going to be over the reactants of A times B raised to its coefficient, which is squared. So let's look at another one. Let's say I have AS406 solid reacting with carbon, 6 carbon solid to make AS4 in the gas form, plus 6 carbon monoxides in the gas form. Again, the equilibrium constant is the product over the reactants. So it's going to be AS4 times CO to the 6. But here's where you got to remember the other thing I said. In that we only include aqueous and gas. So technically that's over 1. Because both of the reactants are solids. So another way that it's more typically written is, since it's over 1, just write the numerator. Questions? Equilibrium expressions are easy, as long as you remember don't include solids with the pure liquids. And it's products over reactants. Okay, let's look at another item though. And we're going to get more, we're going to actually start using this information. A mixture of 9.22 mole of A, 10.11 mole of B, and 27.83 moles of C is placed in a 1 liter container. The reaction is allowed to reach equilibrium. At equilibrium, the number of moles of B is 18.32. Calculate the equilibrium constant. Given A plus 2B goes to form 3C. And they are all in, we're going to say gas form. Okay, folks, when we start getting around to making compounds and messing with compounds, what you're going to do is you're going to develop an ice chart. Now, I call it by, and some people will call it a rice chart. They're the same thing. If you call it a rice chart, it stands for reaction, initial, change, and equilibrium. Some people just leave off the reaction piece. So when you read through this, it says initially you have 9.22 moles of A in 1 liter. Well, that means you have a 9.22 molar solution of A. You have 10.11 moles in 1 liter of B. I'm going to stop writing the molarity and you have 27.83 moles of C. Now we don't know this for certain, but let me ask you which way a reaction typically goes. Which way do you expect a reaction to go?
Right.
To the right. So are you losing or gaining reactants? You're losing, and how do we recognize a losing?
Negative.
Negative. And are you gaining or losing product? And we recognize gaining with positive. Now, according to this reaction, we would lose 1 A. We would lose 2 times B. And we would gain 3 times C. So far, so good. Now, it gave us a hint that at equilibrium, B wound up at 18.32. So the first thing we're going to need to do is figure out what C and A wound up as, and then we can do our equilibrium expression. So the way we're going to do this is we're going to focus on our B here. B 10.11 minus 2x has to come out equal to 18.32. We guessed wrong, basically. Minus 2x is equal to a negative, like, no. 10.11. Now it's equal to 18.32. So our 2.1, sorry. So when we get through with this, X is equal to negative 4.105. So now we can figure out A, because A was equal to 9.22 minus our X of a negative 4.105. And we can figure out what question mark is equal to. Which comes out to be 13.325. And finally, we can figure out C. C we had is 27.83 plus 3x, which is plus 3 times a negative 4.105 is equal to what? $15.515. Any questions so far? We're almost done with the problem. So all I did was plug in X once I found X. Even though it was a negative number, I still plugged in that number in for X. So now we can write our equilibrium expression. It was products C raised to their coefficient over the reactants raised to their coefficient. But we know what these numbers are equal to. So C was 15.515 cubed divided by A, which is 13.325 times B, which they gave us in the problem, is 18.32, and that would be squared. So your equilibrium constant is 0.835. And what does it mean? There's 4 reactants, but it's almost perfect amount because it's almost 1. With that, I will see you on Monday and we'll do more of this. You can expect on the, okay, you'll see me tomorrow. You can expect reaction mechanism and equilibrium expressions on this homework, but I won't do this last piece. I'll start with another one of those first thing in the morning or first thing in the Monday.
Okay, I got behind. So we're literally.
So you literally take that and take.
Okay, so it's just.
Yeah.
Okay, I just want to make sure I knew, like, so one of them will always have all the parts.
Well, in this case, we'll do some later, but if we're needing the equilibrium constant, then yes, I have to give you enough information that you solve the constant. Yeah, and I'll show
Okay.
this, but we'll talk about how to get X's later on.
Okay, at least, thank you.
Here is my